And I also need to teach you about another equation. This time it's called the equilibrium law expression, sometimes the equilibrium expression law. Again, it's an equation that governs an equilibrium reaction. And it is related to rates. Essentially, I need to define it, then I essentially need to show you how we get it from an equation. All right. So there is a statement of the equilibrium expression law, or the equilibrium law. Sometimes I call it the equilibrium expression. And I don't usually say law. Let me just give you a guide to where and what you're seeing. In this equation, the lowercase letters represent the coefficients of the equation, of the balanced chemical equation. The capital letters represent the identity of the chemicals. And through study of an equilibrium back in the late 1800s, chemists experimentally found that when you're dealing with an equilibrium reaction, this mathematical statement is always true. Originally it was called the law of mass action, because they really didn't know why it was true. They didn't know why some chemical reactions didn't go to completion, that some chemical reactions kind of went so far and then stopped. They didn't know about the concept of equilibrium. They were just doing the chemistry. But they found that with these reactions that didn't go to completion, that didn't run its course, that when it stopped, this mathematical expression was true. And this mathematical expression reads, the concentration of C to the exponent lowercase c, which comes from the coefficient of the chemical reaction, times the concentration of D to the exponent D over the concentration of A to the exponent A times the concentration of B to the exponent B. In a more general sense, it's equal to the concentration of the products to some exponent, whatever those exponents are in the, in the equations, over the concentrations of the reactants to some other exponent, whatever their exponents are, or whatever their coefficients are in the balanced chemical equation. And these concentrations are equilibrium concentrations. That's when that statement is true. That statement is true at equilibrium for a particular reaction at a particular temperature. K we call the equilibrium constant. A, B, and C must be in the gas state or in the aqueous phase, must be dissolved. And that's because they must be concentrations. You can't actually change the concentration of a solid or a liquid, and I'll talk about that in a moment. So you can only put gases or aqueous solutions in this equation. You actually ignore or do not put in solids or pure liquids. They are the equilibrium values, so they will be found on our E line. These are all the E numbers. And A, B, C, and D are the coefficients from the balanced chemical reaction. Okay? Let's just practice a few of them and see if we can write them down and see if we can make some sense out of it. And this is really just the beginning of it. We won't get to any calculations today using this equation, but that's where we're heading, right? And again, just to give you the heads up, We now have two mathematical expressions that have E values. We have the ice table, which has E values, and we have this expression, which has E values, which means you've got two expressions. We're going to be combining those expressions, and we're going to eventually be doing math using both. The E values from the ice table are going to go into there, and then we get to do all kinds of fun math. For the reverse reaction, let's say that we wanted to look at this reaction from the opposite direction. And hopefully you could come up with it. It's just products over reactants. It's always products over reactants. So, K reverse. Somebody tell me. Concentration of what to the exponent what? Yep, what do you got? Yep. Yep. Perfect. I got you. I knew you found the trend. It was great. Good job. How does this compare to the previous expression we just wrote down? What's the difference between the one on the previous slide and this one? Yep. It's the reciprocal, right? Or the inverse. It's the inverse. That's always true. If you know the K value for a certain reaction, and then in a later question or a later situation you're looking at the reverse reaction, you can say that the K of the reverse reaction is 1 over the K of the forward reaction. It's just the inverse of it. Okay? I've been doing that all along. Okay? A lot of K's going on here. Again, keep in mind, K is constant for a given equilibrium, for a given reaction, at a given temperature. The temperature changes the K. We'll talk about how that works. But we already know that the temperature changes the rate of a reaction. And if you change the temperature and the forward rate changes and the reverse rate changes, you could, in theory, get this number to become different. Let's do some example situations. First, let's talk about a homogeneous equilibrium. In other words, all of the reactants and products are in, look at that, and I gave the answer away. That's no fun. I should have removed that so you could do that for yourselves. Freeze the slide and see if I give it away next time, too. Freeze. What the? All right, nothing magical here. They're all gases, which means they're all included in the equilibrium expression. Product, concentration of the product, squared over the concentration of the reactant times the concentration of the other reactant. Nothing earth-shattering there. No questions on that, is there? Okay, let's now just talk about a heterogeneous situation. Again, use the proper double-headed arrows if you think of it. If you don't, it's not critical. It's not an emergency in any way. But there is a proper way to do that. Now that I know where to find that, I should fix them all. Now, I'm going to guide you on this one. You might think that the equilibrium expression law should contain all of these things. And so you might think it should contain the calcium oxide and the calcium carbonate, but they're solids. And you don't include the solids in there. All right? I'm going to write them in, but then I'm going to get rid of them. I'm going to show you why we get rid of them. So if you were to say that the concentration of CaO times the concentration of CO2 over the concentration of CaCO3, the reason we don't include the solids is because for pure solids and pure liquids, their concentrations are constant. It means that this number right here is a constant value. And this number right here is also a constant value. And I'm going to describe to you an example of where where I can show you that nice and easily. If the concentrations of pure solids and liquids are constant values, then those constants can be absorbed into the equilibrium constants. We don't really need to keep all these separate constants. So for a heterogeneous reaction, we only include the gases or the aqueous, and therefore the K is simply equal to the concentration of CO2 gas. All right? It's that simple. Oh, sorry, you don't include the G. I don't know why I put that there. It's simply equal to the concentration of CO2, because it is a gas. So you don't include solids or pure liquids in your equilibrium expression law. I'm looking at the clock. I got about 4 minutes left, and I'm going to give you another example on why we don't. And I'm going to advance the slide once you're done writing there, and it has a little bit of homework problems on how to write down equilibrium expression laws. The easiest homework you've come across in a long time. And then I'm going to stop the recording and I'll show you this other example. Oh, we were going to do some examples, but no, I'm going to bring it right to there, because again, the time's going to run out.